Hi, my name is Max Croci, and today I'll be talking about online parameter inference for the simulation of a Bunsen flame using Bayesian neural network ensembles. This work was done in collaboration with Ushnish Sengupta and our supervisor, Matthew Juniper. As an outline, I'll first talk about the Bunsen flame experiment and our model for the flame. I'll talk about our aim, which is how to render the model quantitatively accurate. We'll also talk about the state-of-the-art solution to this problem and our proposed alternative. We'll go through some results before also touching upon some future work. Our experiment comprises a Bunsen flame placed inside a glass tube. A high-speed camera takes photos of the flame inside the tube, and this flame is perturbed or excited using a loudspeaker connected to an amplified function generator. We can also vary the flame chemistry, the gas composition, and flow rates. Our data looks like so, effectively a sequence of images of the flame. Our flame edge model is called the G equation, introduced by Williams. It is a partial differential equation which describes the flame edge as a quantity G, or where G equals 0, where G is a scalar field, two-dimensional in our case, it also has a time component, and the flame edge is considered to be the G equals 0 contour of this field. Areas of negative G are the reactants, and areas of positive G are the products. The flame travels normal to itself with laminar flame speed SL, and this speed depends on both the flame chemistry and also the local curvature. The flame also wrinkles and cusps under a velocity profile, which comprises a steady-state base flow profile in the vertical direction and small velocity perturbations added in both the vertical and horizontal direction. This model has 6 tunable parameters. The first 3 are the flame radius, the flame aspect ratio, and the flame Markstein length. The Markstein length governs how curvature perturbs the flame edge. These 3 parameters are valid both in the steady state or unperturbed setting, as well as the perturbed setting. And the next 3 parameters are the velocity perturbation Struhl number, amplitude, and wavelength, whereas the Struhl number is the non-dimensional frequency. And these are of the velocity perturbations. Our aim is thus, how can we tune the parameters of the model to best fit the experiments? So from the experiments, we have time series of images of the flame. We can pre-process them to detect the flame edge. And how do we tune our parameters so that we can simulate and forecast using the G equation this flame in space and time? We use a program called LSGen to solve the G equation and iterate it through time. And this was developed by Santosh Hemchandra. The state of the art for this is the ensemble Kalman filter. How this works is it uses Bayesian statistics to combine model forecasts with experiments. So these plots here represent the flame experimental data shown in black, and in yellow, the most probable location of this flame. And the Kalman filter takes the sequence of data, experimental data, and gradually improves its estimates of the flame parameters until convergence. The 2 parameters it estimates are the perturbation amplitude and wavelength, so only 2 out of the 6 parameters. It is prohibitively difficult for the Kalman filter to estimate the other 4 parameters. And this is a main limitation of the state-of-the-art. Additionally, this process typically takes 2 hours to converge on a laptop. And this is so for every different flame time series data set. So for example, were we to change the flame chemistry or the gas flow rate, we would have to repeat this process. And every time we want to do this, it'll take hours to converge. Our method is an alternative whereby we propose to create a library of simulated flame edges with known parameters using our program LSGen. We define or set approximately 8,500 different parameter combinations, and we use LSGen to iterate the G equation until convergence to produce simulated flame edges. And this process is easily parallelized and takes approximately 2 hours per computer core per flame edge. We have a computer cluster which we have access to, where we can do the parallelize this method and produce hundreds of flame edges sequences per hour. With this library created, we train neural networks to learn the parameters from the flame edges in a supervised setting. This takes approximately 1 hour of training on a standard GPU. Upon convergence, the neural nets can infer all 6 parameters from just 10 flame snapshots. And I'll talk about the neural network architecture now. And inference also, of course, a big benefit of neural networks is they make predictions extremely quickly. Now, our neural networks look like this. They comprise an input layer, which is a concatenated vector of the coordinates of the flame edge for a sequence of 10 flame images. So each vector represents a sequence of 10 images where we have just used the coordinates of the flame edges. This is then passed through fully connected layers, 4 hidden layers. And then we have 2 output layers, a mean layer and a variance layer. The mean layer estimates or produces an estimate for each of the 6 parameters. And the variance layer produces an estimate of the noise in these estimates. This is otherwise known as the aleatoric uncertainty. So if the neural network is confident in its predictions, it will predict a very small noise level for the particular parameter. Whereas if it is uncertain, it will produce a very high noise. Additionally, we also use neural network ensembling, where we use 20 neural networks, and we use these to quantify the epistemic uncertainty in the predictions as well. The epistemic uncertainty is also known as the model error. And this arises due to the fact that having for example, two different neural networks trained on the same data, but initialized with different weights and biases, tested on unseen data, these neural networks will give different predictions. And so the variance of these different predictions is used as the epistemic uncertainty. Now I'll show you some results. In the top row, each time we have our raw data, which are a sequence of flame images. Just below, I've shown the resulting of the pre-processing, which is very fast, and it's just to find the flame edge. And next we see the results of the Kalman filter, where the Kalman filter has estimated 2 of the parameters, and we've used these parameters to re-simulate the flame in our simulator. And we see a very good fit between the black dots, which are the flame edge, and the green band, which is the Kalman filter's most likely location of the flame edge. And beneath that, in the exact same way, the re-simulated flame using the Bayesian neural network ensembles parameter predictions. Lastly, we plot the normalized surface area variation of the flame edge over one period. This is an important quantity to find, as it is a proxy for the heat release rate of a flame or the combustion process. And that in itself is key to quantifying the flame transfer function, which is the ratio of the flame heat release rate to velocity perturbation, which is a key quantity to know in thermoacoustic analyses. We have estimated manually or ad hoc the flame normalized area variation. And we see that both the Kalman filter and Bayesian neural networks give good estimates of this. And as well as the uncertainties, the Bayesian neural network ensemble actually has much higher uncertainty in its predicted area compared to the Kalman filter. And this is in part due to the fact that the Bayesian neural network ensemble only looks at 10 images at once and produces parameter estimates, whereas the Kalman filter will take as much data as is available before converging to parameter estimates. So the strengths of this proposed method are that once trained, the ensemble infers the parameters of the model extremely quickly. The ensemble can also infer the parameters for any number of different configurations. So for example, if we were to increase the gas flow rate or change the chemistry or change the perturbation amplitudes, we wouldn't have to recreate a library and retrain the neural networks. This method is actually general, and we can generate parameter estimates extremely quickly, assuming the correct parameters lie within the library ranges. A weakness, however, is that because only 10 snapshots of data are used, that we get high uncertainty in our predictions. Now, one obvious way to fix this would be to use just more snapshots in our input, but unfortunately, this would increase the size of the neural networks, which would lead to more expensive training and more expensive memory requirements. Our future work will consider different burner geometries. For example, the Volvo burner, which is a V-shaped flame stabilized on a notch, which is also only partially observed. We don't see the whole flame length, we only see a section of it. And it's far more noisier than our original Bunsen flame data. So here what I've shown is our original data, where we've detected roughly a flame edge, which we have also smoothed. And on the right, I show the results showing the most likely flame position using parameters estimated by the neural networks trained on a library of flame edges of this type, of this V type. And this method can also be used for other burner geometries, which we will investigate. To summarize, our aim was to infer the parameters of a flame edge model from experimental data. We propose using neural network ensembles trained on a library of simulated flame edges. Once trained, this method produces comparable results to the ensemble Kalman filter, which is the state of the art. Future work will consider different architectures to use all the data, for example, recurrent architectures, and this method will also be applied to different burner geometries. Thank you very much for listening, and I hope you enjoyed the talk.